Hello, my name is Sheldon Grover. Today I will be discussing reactions of alkanes, alkenes, alkynes, aromatic/cyclic reactions, electrophilic substitution reactions, and nucleophilic substitution reactions. We will begin with reactions of alkanes. Alkanes are the least reactive hydrocarbons. Alkanes are generally unreactive. In this presentation, I will write equations which represent complete and incomplete combustion reactions. Then, I will describe the free radical mechanism for the equation of alkanes as you were. I will describe the free radical mechanism for the reaction of alkanes with halogens. Alkanes are saturated, which means they are already full. We have to break some bonds and remove some atoms before more atoms can be put into the molecule. So one way to explain why they are so unreactive is to look at bond enthalpies and bond polarities. High bond enthalpies means that bonds are difficult to break. Carbon-carbon single bonds and carbon-hydrogen single bonds tend to have high bond enthalpies, so they are hard to break. With bond polarities, due to electronegativity differences, between atoms, which leads to an imbalance of electron density around the molecule, reactions tend to happen due to high or low electron density. The bond between carbon and hydrogen are very similar in electronegativity, which make them not very polar. Due to this, these molecules do not react very well or very much. So, in a nutshell, because the bond enthalpies are very high and their bond polarities are low, alkanes tend to be unreactive molecules. Now let's look at reactions that they do take part in. Remember, all hydrocarbons, not just alkanes, can burn very well, which is why we use them as fuels. In thinking about how to write equations for this, any alkane can be used. Here's an example with methane, but remember, we are talking about complete combustion, which means that the carbon and hydrogens get as much oxygen as they can when it comes to the products. Due to the carbon in methane getting its maximum amount of oxygen, it forms CO2, and there is only one oxide of hydrogen, which is water. As always, with any chemical equation, once you form your products from your reactants, you balance your chemical equation. In any complete combustion reaction, these will be the products: carbon dioxide and water. It may appear easier to balance this when the number of carbons in the hydrocarbon is an odd number, like with methane. But here's the same reaction using ethane with an even number of carbon atoms. As seen from our equation, any alkane that contains an even number of carbons, you'll end up with an odd number of oxygens in the product. From our reaction, 3.5 oxygens are in the reactants, which is fine, but many chemists prefer whole numbers. So to get a whole number, you simply need to double everything in the equation. In summary, all combustion reactions of alkanes contain carbon dioxide and water as their products. In contrast to complete combustion reactions, incomplete combustion reactions lack oxygen, is a lack of oxygen, have a lack of oxygen. Due to this lack of oxygen, incomplete combustion reaction products will be carbon or carbon monoxide, and how much carbon or carbon monoxide you produce depends on how much oxygen you have. Now we must, as always, we must balance our chemical equation. So, in summary, incomplete combustion reactions lack oxygen, and due to this lack of oxygen, the carbon in the alkane could be left as carbon. It also turns into carbon monoxide, a very poisonous gas, rather than carbon dioxide, which is formed from complete combustion reactions. How much carbon or carbon monoxide you produce depends on how much oxygen you have. This type of reaction could happen in a Bunsen burner where the air hole was closed. There wouldn't be much oxygen, so the methane would turn into carbon and water. The carbon would be black soot, which is what would be all over the beaker that was being heated. To react alkanes with halogens, hydrogens must be swapped with the halogen. It's a tongue twister. Let me try that again. To react alkanes with halogens, hydrogens must be swapped with the halogen, as seen in both of these reactions. Alkanes are excellent at burning, but other reactions not so much. In particular, reactions with halogens. To react an alkane with an halogen, a substitution must be performed. These are called substitution reaction due to our swapping one hydrogen in the hydrocarbon for a halogen atom. Alkanes will react with halogens, but to do this, bright light is needed. Therefore, UV is often placed above the reaction arrow, right here and right here. As you can see, the CH4 loses hydrogen but gains one of the bromine atoms, and we're left with HBr, or as seen with the ethane, it loses hydrogen but gains chlorine, and we're left with HCl. Writing the reactions is easy, but we must understand how we got our products, meaning we need to know the mechanism of how we got our products. With free radical mechanism, the first step involves the formation of a free radical. This is called the initiation step because it is what gets everything started and why we need the UV light above the reaction arrow. For example, a bromine molecule could turn into two bromine radicals. The radical is represented by having a dot. That means it has an unpaired electron. The UV light causes this split to happen. This type of bond breaking being fission, is called homolytic. Homolytic fission is a chemical bond dissociation of a molecule by a process where each of the fragments retain one of the originally bonded electrons. This free radical is extremely reactive because they want to find a partner for this electron, which means they will react with an alkane, which is not very reactive. This free radical reacts with the methane and makes HBr. This is the propagation step. This step takes one of the electrons from the carbon-hydrogen bond and makes the HBr as seen in the previous slide. What is left is CH3 because it has lost a hydrogen atom, but now has an unpaired electron. It is called propagation because although we used up one radical, we made another. Now this radical can react with something else, like another bromine molecule. And if it did that, then this electron would pair up with one of the electrons from this bromine bond and make CH3Br and produce another bromine radical. Where that radical could take place in another reaction. That is why this is called propagation. Because although we used one radical, we made another. The last step, if you notice that we made HBr and CH3Br, is called the termination step. In this step, it is where two radicals collide, because if two things with unpaired electrons come together, they won't produce another radical. They will produce something that has all paired electrons, and that is the end of the reaction. Now we will go into reactions of alkenes. First, I shall briefly go over some alkene reactions. Then I will go further into what is actually happening. Hydrogenation. The alkene reacts with H2 and Pd, which is palladium. This is a syn addition. Hydrohalogenation. The alkene reacts with HX, the X being chlorine, bromine, or iodide. Halogenation. The alkene reacts with two halogens, bromine, Br2 or Cl2, in an inert solvent, CH2Cl, and this is an anti-addition. Halohydrin. The alkene reacts with two halogens, Br2 or Cl2, in a polar solvent such as water, and the solvent is part of the reaction. This is an anti-addition and also a Markovnikov addition. Acid catalyzed hydration. The alkene reacts with water molecule and an acid catalyst. This is a Markovnikov addition. Oxymercuration. The alkene reacts in step 1 with HgOAc2 plus H2O. And in step 2, NaBH4. This is a Markovnikov and anti-addition. Alkoxymercuration, the alkene reacts in step 1 with HgOAc2 plus ROH, and in step 2, NaBH4. This is a Markovnikov and anti-addition. Hydroboration. The alkene reacts in step 1 with BH3 and THF, and in step 2 with NaOH and H2O2. This is an anti-Markovnikov, but a syn addition. Epoxidation. The alkene reacts with RCO2H, which is a per acid. This is a syn addition. Dihydroxylation. The alkene reacts with KMnO4 under weak conditions in cold temperatures with a dilute solution. This is a syn addition. Also, a second dihydroxylation reaction can be performed. The alkene reacts with OSO4, which is osmium tetroxide, which is a syn addition. And then we have cyclopropanation. The alkene reacts with CH2I2 in a zinc copper catalyst, and this is a syn addition. Now let's go further into the reactions I just named. Hydrogenation, which is a catalytic reduction. In this reaction, the alkene is reacted with H2 in some metal catalyst like platinum or palladium. The trick here is to break the pi bond and add hydrogen to each of the carbons, keeping in mind that this is a syn addition because of the metal catalyst grabbing the pi bond. The pi bond is grabbed from the same place, meaning both carbons are grabbed together, so the hydrogen will be added to the same side. In this reaction, hydrogenation, the hydrogens that are added after the pi bonds are broken would be shown with wedges on the same sides of each hydrogen or dashes on the same side of each hydrogen, because this is a syn addition. Hydrohalogenation. This comes from hydro, meaning hydrogen, and halogen, meaning X. You will see this reaction written out as HX, reacting in some inert catalysts. With this reaction, the pi bond is broken and the hydrogen is placed on the less substituted carbon. What is shown in the example is an alkyne, but the reaction is the exact same for an alkene, which is what we're discussing at present. Halogenation. Halogenation reaction is very similar to hydrohalogenation, except without the H. We're adding two halogens, for example, Br2 or Cl2. In this case, we will react the Cl2. The key is to break the pi bond and put one halogen on either carbon that used to be the double bond. This reaction is an anti-addition, meaning they will add to the opposite faces of the pi bond due to the chloronium intermediate. The bridge will block whatever face it's on, so that the other halogen has to be added to the opposite. With the shown example, you can't tell, but dashes and wedges are used to show that this is an anti-addition for chirality sakes. This reaction is in an inert solvent, meaning the solvent doesn't react. Halohydrin. With the halohydrin, everything is the same except that we use a polar solvent such as water. The reaction starts the same. You would break the pi bond, but this time the solvent will also participate in the reaction, adding to the more substituted carbon. The hydrogen is placed on the less substituted carbon, and you take your solvent, drawn out as HOH, and deprotonate it and add the rest of that group, OH, to the more substituted carbon. The product is a halohydrin, meaning halogen is on the less substituted carbon, and the solvent minus the hydrogen is on the more substituted carbon. That gives us the halo for halogen and the hydrin for water, or in this case, OH. This is an anti-addition and would be shown with dashes and wedges that are not shown in the example. Acid catalyzed hydration reactions. For acid catalyzed hydration reactions, think of water for hydrate. We're adding H2O to the molecule and we're using an acid catalyst. You'll see this written as H2O, H3O plus, water and acid like H2SO4. All this tells you is that we're adding the OH. So you want to break the pi bond, add the hydrogen on a less substituted carbon because it's a Markovnikov addition, and keep in mind the carbocation intermediate, which would form on the more substituted carbon. The product of this reaction has hydrogen on the least substituted carbon and OH on the carbon that held the final carbocation intermediate. Next, we'll discuss oxymercuration and alkoxymercuration together. We shall look at oxymercuration and alkoxymercuration at the same time. Both of them have both of them have oxy for oxygen, merc for mercury, and the only difference is we have an alkyl group in the alkoxymercuration reaction. The reagents are nearly the same for both of these reactions. The key here is the merc portion in the name, and that is mercury. We'll show HgOAC2. The difference for oxymercuration, the difference is for oxymercuration, we're adding H2O. And for alkoxymercuration, we're adding an alkyl chain shown as ROH. Step 2 is sodium borohydride, which is NaBH4. The trick here is to recognize that this is a Markovnikov reaction, meaning we have a semi-carbocation intermediate, but mercury does not allow the carbocation to shift, even though it is a Markovnikov. Even though it is a Markovnikov, we have no carbocation rearrangement. We break the pi bonds, put a hydrogen on a less substituted carbon. In oxymercuration, we add OH on the more substituted carbon. In alkoxymercuration, we add OR. Given the mechanism of this reaction, it's Markovnikov and also an anti-addition. That means that if you have to show chirality, the H and the OH will add to the opposite faces. One is a dash and one is a wedge. Hydroboration oxidation is another hydration reaction, but this one is an anti-Markovnikov reaction. This one is an anti-Markovnikov, where the previous ones we looked at were Markovnikov. For this reaction, we are using BH3 and THF in the first step, and NaOH and H2O2 in the second step. This is an anti-Markovnikov reaction, meaning the hydrogen adds to the more substituted carbon, but the alcohol adds to the less substituted carbon. However, they add to the same face of the pi bond, making it a syn addition. That means if you're showing chirality, the H and the OH will both be dashes or wedges. Next, we will discuss epoxidation reactions. In this reaction, the alkene is turned into an epoxide by reacting it with a per acid. A per acid, per means extra oxygen. This will look like a carboxylic acid, but instead of an RCO2H, it will be an RCO3H, where the third oxygen makes it the per acid and gives you the peroxide. The trick here is to break the pi bond and place the oxygen between the two carbons, and also imagine that the pi bond reaches out and skewers that oxygen so that it is attached to both of those carbons. Since the oxygen is attached to both carbons, that makes this reaction a syn addition, because the oxygen has to be connected to the same side of both of those carbons. Dihydroxylation reactions. In dihydroxylation reactions, the product will be be a syn addition, meaning that the OHs will add to the same face of the pi bond. The first dihydroxylation reaction is reacting KMnO4 under weak conditions in cold temperatures with a dilute solution. The second dihydroxylation reaction is reacting OSO4 osmium tetroxide. These reactions will break just the pi bonds and add the OH on each of the carbons on the same face of the pi bonds. If chirality is shown, both OHs will be either dashes or wedges. Cyclopropionation. The name implies we are creating a cyclopropane, which is a 3-carbon chain. For this reaction, we are reacting CH2I2 in a zinc-copper catalyst. In this reaction, the pi bond is broken and the ring is created just as with epoxidation. But this time, we are using carbon instead of oxygen to create the 3-membered ring. The key here is to remember that the substituents on the carbon have to be 2 of the same, and 2, that you have to remove at least 1 halogen. If we have to remove 1 halogen for this Simmons-Smith reaction, and the group that we add the carbon to have to be the same. We cut out both halogens, leaving us with 2 hydrogens. I know that was a tongue twister, so let me say that again. The key here is to remember that 1, the substituents on the carbon have to be 2 of the same, and 2, that you have to remove at least 1 halogen, at least 1 halogen. If we have to remove at least 1 halogen for this Simmons-Smith reaction, and the group that we add the carbon have to be the same, we cut out both halogens, leaving us with 2 hydrogens. When you see 3 halogens, such as CHCl3, 2 of them stay on your product. When you see 2 halogens, such as CH2I2, none of them stay on your product. Given that this product has the ring, it is a syn addition because there is no other way to add the ring. Now we shall go into reactions of alkynes. Alkyne summation. Alkyne reactions are the exact same as alkene reactions, except that alkynes have carbon-carbon triple bonds. During alkyne reactions, the alkyne becomes alkenes or alkanes, depending on how many atoms are added. Due to the similar nature of alkynes and alkenes, I will not show an abundance of alkyne reactions. The next slide will simply show a few alkyne reactions to display their similarity. Take a look. As we can see, the carbon-carbon triple bond is broken and a carbon-carbon double bond is formed. But it can also be broken down to an alkane, where the carbon-carbon double bond of the alkene is broken, and you see the carbon-carbon single bond of an alkane, which is exactly what I explained before with the alkene reactions. Next, we'll discuss reactions of aromatic/cyclics. Although this slide is a bit difficult to view, it is simply to display the reactions aromatics can have. A more clear depiction of this roadmap may be viewed at the link shown above. I'll let you take a moment to write that link down if that's what you would like to do. Okay. We shall begin by discussing aromatic substitutions, which can be electrophilic or nucleophilic. To discuss substitutions, you must understand what an electrophile and a nucleophile is. An electrophile, electron loving, is a reagent attached to electrons. Electrophiles are positively charged or neutral species having vacant orbitals that are attached to an electron-rich center. Nucleophiles, from nucleus loving or positive charge loving. A nucleophile is a reactant that provides a pair of electrons to form a new covalent bond. Electrophilic aromatic substitutions. The reaction begins when one of the pi bonds break out of a stable aromaticity and reaches for the electrophile and creates a new bond. The other carbon that used to hold the pi bond is now deficient and is going to have a positive charge. This intermediate, while it still has resonance, is no longer aromatic. This is for two reasons. Reason number one, we no longer have resonance going in a complete circle. And reason number two, don't forget that hydrogen, which means the carbon where the electrophile added now has two bonds to the carbon, one to the electrophile and one to the hydrogen. It is sp3 hybridized and is no longer planar. In order for this molecule to be stable again, we have to remove that hydrogen and reform the aromaticity. This is accomplished by bringing in a weak base and grabbing that hydrogen, but only the nucleus. When the hydrogen is grabbed, the electrons that bind it to that carbon will collapse back into the ring in the direction of that positive charge. This reforms the aromaticity of the ring. The non-aromatic resonance intermediate is called the sigma complex. Remember, resonance only exists on paper. With resonance, you always want to find something that is very negative, such as a lone pair or pi bond, and move it towards something that is positive. In this case, the carbocation is going to draw the resonance. In the first resonance structure, the pi bond directly near that carbocation takes the electrons and attacks the positive carbon. We then draw a double-headed arrow to imply that this is a resonance structure. And the new structure is drawn. One pi bond hasn't moved, but the other pi bond is now sitting where the carbocation used to be. The other carbon that used to hold the pi bond is now deficient and gets a positive charge. Now we can go back to the original structure, but there is no need. The double-headed arrow shows this is possible. Now, in the second structure, the pi bond that did not move in the first structure attacks the positive carbon, shifting the pi bond in the ring. Once again, a double-headed arrow shows this is resonance. The carbon that used to hold the pi bond is now deficient and gets a positive charge. These are the three resonance structures for the sigma complex. To show that they are resonance, the entire thing is placed in brackets. Nucleophilic aromatic substitutions. This reaction only recurs when you have a halogen and a strong electron withdrawing group, or moderate electron withdrawing group in the ortho or para position relative to the leaving group, and the leaving group is the halogen. In the reaction shown, we have a strong electron withdrawing group in the para position relative to the chlorine, and we're substituting an OH group into the system. In this reaction, the OH forms a bond to the carbon, the chlorine. In this reaction, the OH forms a bond to the carbon the chlorine is attached to. A pair of electrons that is directly next to the carbon that the chlorine is attached to comes off and joins the carbon to the right of the attachment. The intermediate for this reaction is a carboanion due to the negative charge. What happens, shown in resonance discussed previously, is a double bond is regenerated in the ring and the chlorine comes off. This leaves us with the product of OH connected to the ring with a strong withdrawing group in the pair position. Plus, not shown in the example, you have your chlorine negative because the pair of electrons is now with the chlorine. Alkyl benzene oxidation reactions. This slide simply shows when KMnO4 step 1 and H3O plus heat step 2 is added to the alkyl benzene, benzoic acid is formed. This is due to a very strong metal base oxidizing agent that selectively oxidizes the benzylic position because there is a benzylic hydrogen there. The first step of these reactions involve a metal oxidizing at the benzylic position to remove a hydrogen. This forms a very stable benzylic radical. Multiple steps after that results in the benzoic acid. The only exception to this is tertiary alkyl groups. With those, there will be no reaction as seen on the slide. This is due to there being no hydrogen at the benzylic position. Aromatic reduction reactions, Birch reactions. The Birch reduction is an organic reaction which is particularly useful in synthetic organic chemistry. The reaction was reported in 1944 by the Australian chemist Arthur Birch. With the Birch reduction reaction, we start with benzene. We are going to react it with an alkyl metal like sodium, Na, and a liquid ammonium, NH3, and follow that with an alcohol, ROH, to get our final product of 1,4-cyclohexadiene. Sodium has one valence electron. The reaction begins with sodium donating its one valence electron to the benzene ring. Once that happens, electrons in the ring also shift. The shifts produce an anion and a radical anion seen in the second ring after reaction arrow. Next, the alcohol functions as an acid and the anion, which is functioning as a base. Those electrons pick up a proton from the alcohol as seen in the third ring after the reaction arrow. Next, more sodium donates its valence electron to the radical, and an anion is produced. The last step is another acid-base reaction, where the anion, functioning as a base, picks up a proton from the alcohol, and we have our final product. Hydrolysis. I will be honest with you, I couldn't find much explaining hydrolysis of aromatics. Therefore, this slide will simply explain to you what hydrolysis is and show you a reaction involving hydrolysis. Hydrolysis is a reaction involving the breaking of a bond in a molecule using water. In chemistry, there are three main types of hydrolysis: salt hydrolysis, acid hydrolysis, and base hydrolysis. As seen in the reaction shown here, the nitrile or amide group can be hydrolyzed to a carboxylic acid group. Acylation reactions. In this reaction, benzene reacts with an acyl group, other known as an acid chloride, in the presence of a catalyst such as the AlCl3 Lewis acid to form an acyl group on the benzene ring. The molecule that adds the benzene is an acyl group, or acid chloride. In this case, we have an acid chloride. This is a carboxylic acid derivative, where we replace the OH from the carboxyl with the chlorine. The chlorine from the acid chloride attacks the aluminum, resulting in an aluminum atom with a total of 4 bonds and 8 electrons and a formal charge of -1, and a chlorine atom with 2 bonds and 4 electrons with a formal charge of +1. Chlorine as a halogen is highly electronegative and dislikes that positive charge. To compensate, it will grab electrons from the carbonyl carbon, break the bond, and take electrons for itself. The resulting AlCl4 still has a negative charge on the aluminum, but the chlorine is now neutral. The acyl group now has an incomplete octet and a positive charge due to chlorine leaving. Through resonance, an acylium ion is formed. Due to the carbon in the acylium ion being partially positive, the benzene attacks it. The electrons were being drawn toward oxygen. The electrons that were being drawn toward oxygen are now able to completely break away from carbon and rest as a lone pair on the oxygen atom. The resulting intermediate has a neutral carbon double bond to oxygen and single bond to an R group. We also have an hydrogen on that same benzylic carbon atom, making it an sp3 hybridized and incapable of resonance. Finally, we have a positive charge on the other carbon on the benzene where the pi bond broke away from. To reform aromaticity, we bring back the AlCl4-, specifically the chloride that was on the original ring. The chlorine will break away from the aluminum and use those electrons to form a bond between itself and hydrogen. It only reaches for the hydrogen nucleus, leaving the electrons to collapse away from the hydrogen and towards that positive carbon on the benzene. These electrons are what reform the benzene aromaticity, giving us our final product of an acyl group on the benzene ring plus HCl. In conclusion, this concludes my lecture on reactions of alkanes, alkenes, alkynes, aromatics, electrophilic substitutions, and nucleophilic substitutions / additions. Hopefully you found this presentation beneficial.